time. We left off, well, last time we finished up balancing chemical reactions. And the reason why you need to know how to balance chemical reactions is because without the coefficient in the balance equation, you can't make this relationship over here. And the relationship is how one chemical relates to the other, how one chemical here relates to the other. And the only way they do that is through the coefficients in the balance equation. So you need to know how to balance a chemical reaction, because if you're going to do some sort of stoichiometry, and stoichiometry will involve solids right here, or number of molecules, number of atoms, but it's always going through the moles. It's always going through the moles. And reason why it goes through the moles is because, remember, atoms, molecules are very, very small. And so in order to account for these chemicals or these substances that isn't too overwhelming, we need to bundle it in terms of 6.02 times 10 to the 23rd. So that's why we need to go through the moles. But later on in the future, you guys are going to be studying solution chemistry. And again, if you have the concentration and molarity and the volume, you can calculate the moles. And then in the upcoming section, if you have gas phase, then you can use the ideal gas law to calculate the moles. So you can see that whenever we do stoichiometric problems, you must know how to get through the moles if you're going to relate one substance, one chemical to another. Now, it doesn't have to be the reactant to the product. It could be a reactant to a co-reactant, or a product to a co-product, but they're related based on the balance equation. That's why you need to know how to balance the chemical reaction, because if it's not balanced, then your relationship is going to be messed up. So in terms of this stoichiometry map, you want to make sure that you know how to read this. And again, you need to have a starting point and an end point. Okay, starting point I've sort of outlined here in terms of a letter, and that's how I'm going to try and teach it to you today. The letter goes through, and if you want to go from mass of a substance to most of the substance, you have to use these stepping stones, which are your conversion factor. And if you know how to do that, then what you can do is set up dimensional analysis. That's why we emphasize dimensional analysis so much in the beginning of the course, because if you don't buy into dimensional analysis, this whole stoichiometry thing is going to mess you up, because you're going to try and memorize equations. And yes, some people can do it, but for most of us, like me, I best work when I know the logic behind the calculation, and dimensional analysis allows you to do that. So that's why we want to go through this. So I think last Tuesday we talked about the stoichiometry map, and again, if you have one chemical, then you just want to stick to one side. You can calculate based on the mass of that chemical, the moles, and if you have the moles, you can calculate the number of molecules or the number of atoms. If you have the mass of a chemical and that chemical is a liquid, then you can use the density to calculate the mass. And then you can use the molar mass of that substance to calculate the moles. So again, if you're just dealing with one chemical, then you need to do it that way. If you are dealing with a reaction, then what you need to do, of course, is you need the balance equation. And the balance equation is what we covered in chapter 7. So in terms of the stoichiometry map, we talked about this last time, because the reason why I gave this slide was to let you know that a lot of the questions may look different, but they all have the same type of um, strategy in solving. It's all going through that stoichiometry map. So we can give you a lot of questions with variation, but if you know the fundamentals in terms of using that stoichiometry map, then it's not going to phase you, because you already know how the relationship works. So I think we started off with this problem. So this is a problem. Again, I want to illustrate to you that um, we're going to use the stoichiometry map, and I'm going to lay it out so that you guys can follow along and see how the stoichiometry map works and how to set up your work, because really it's a setup and you don't want to take shortcuts in terms of just writing numbers. The key to good science, and if you want to be successful in 200 and 201 and any of your science courses, is to make sure that you pay attention to the details. And the details in stoichiometry is not only the numbers but the units. You have to bring along the units. And the reason why the units are important is because you can easily get lost in the calculations, but the units allow you to figure out what that number is associated with. So let's take a look at this problem. This is a much more detailed problem, but again, as detailed as it is, it's still quite easy to maneuver just based on the fact that we can use the stoichiometry map. This is a case where you have 35 grams of potassium. You have 35 grams of potassium. Sorry about that. That's a problem with these things, is that sometimes the controller is not easily controlled. You have 35 grams of potassium permanganate. That's KMnO4. Okay, and that was the problem. Let's go back real quick. The the question initially was here. You got 35 grams of potassium permanganate, and it's mixed with 45 grams of potassium chloride. Whenever you're given a quantity of two chemicals, then you basically have two problems in one, because you have to figure out how much each of these chemicals is going to yield in terms of the product. And then when you figure out which one produces the less amount of quantity, that's the chemical that's going to run out first. It's called the limiting reagent. And you use that for the rest of the calculation. So in this particular problem that's described, it says you have 35 grams of potassium permanganate, that's this guy right here, KMnO4, and 45 grams of hydrochloric acid. And the question is, how much chlorine is theoretically produced? When you see this word theoretically, it means that if the chemicals were to produce 100% of the product, how much of that product is produced? And the chemical that is going to produce the theoretical yield is the chemical that runs out first. Okay, the second part of this is, if you got 10.3 grams of chlorine, what is the percent yield? Now, I know I covered this last time in our discussion, but I think I rushed through it. The chemicals, the first step you need to do is balance the chemical reaction. Okay, so this is the balanced chemical reaction. Let's double check. It's the first thing that you need to do. We've got two potassiums here. We've got two potassiums here. Okay, remember that the numbers outside refers to the whole chemical. We've got two permanganates here. We've got two permanganates here. I mean, manganese, not permanganate. Permanganate's MnO4. Manganese is Mn. We're going to save the chlorine for last in terms of balancing. And why? Because chlorine is a chemical in which there's only one element involved. So what you want to do is save that as your last step, because by changing the coefficient in chlorine, you only affect the chlorine atom. So that was one of the hints that I talked to you guys about in chapter 7. Here we have 16 hydrogen. 8 times 2 is 16 hydrogens. Then we've got 8 oxygens here. And here you can see that there are 8 oxygens. 2 times 4 is 8. Finally, we balance the chlorine. And here we can see that there are 10 here. And there are 4 here. Remember, you got to account for all the chlorines. And then there are 2 here. See how chlorine is the most complicated atoms to balance? That's why we save it for last, because if you try and balance the chlorine in the middle of this step, you're going to affect other atoms in this process. So anyway, what we have here is 10 plus 4 plus 2, and that's going to be 16. So that's the balance equation. That's the first thing you need to do if you have a stoichiometry problem. Actually, it's not the first thing you do. The first thing you do is make sure that the formula that you write down for each chemical is correct. You got to make sure that the formula is correct. Once you are confident of the formula, then you can balance it. Once you balance it, the next thing you want to do is simplify that problem and start ignoring all the chemicals except those involved in the question. And that means potassium permanganate right here, hydrochloric acid, and chlorine. So what you want to do is ignore all of these. The only reason why you are worried about these chemicals right here is because they're involved in the balance equation. But the problem, the stoichiometry problem, doesn't refer to any of these chemicals. Okay, if it does refer to like water, then you need to pay attention to it. But the way the problem is described, you've got 35 grams of potassium permanganate, 45 grams of hydrochloric acid and chlorine. These are the only chemicals that you need to pay attention to. And notice that these chemicals are KMNO4, HCl, and Cl2. The only time you ever worry about these numbers in front of these chemicals is through the relationship between each other, the balance equation. So when you're asked, what is the molar mass of potassium chloride? Then, sorry, what is the molar mass of hydrochloric acid? Hydrochloric acid is 1 for hydrogen, 35.5 for chlorine, okay? And the molar mass is going to be 36.5. Don't take 36.5 and multiply it by 16. That's a common mistake that I see in a lot of students. 16 just tells you how that chemical is related to the other chemical. The chemical is hydrochloric acid, HCl. The chemical is chlorine, Cl2. Don't take Cl2, 71 or 70.9 and multiply it by 5. If you do that, you're going to mess yourself up. Again, let me emphasize, the only time you ever use the coefficient in the balance equation is when you're relating one chemical to the other. Otherwise, ignore it, because you're going to mess yourself up if you take the if you take the molar mass and you multiply it by the coefficient. The chemical is chlorine, hydrochloric acid, or potassium permanganate, and you need to calculate the molar mass for that. Okay, I think you guys know how to calculate the molar mass for these guys um, based on earlier chapters. So let's go ahead and see how to set this particular problem up. Okay, got to get out of this mode real quick. Let's see. So when we set this problem up, you can see that what I've done was put the molar mass of the chemicals I'm interested on at the very top, because you want it out of the way. And then I put the information that the problem presents itself in the bottom. 35 grams for potassium permanganate, 45 grams for hydrochloric acid. And then the question is, what mass of chlorine? So the next thing I do is I break this problem into two. I work first with potassium permanganate, okay, and I figure out how much chlorine is produced. So I do that based on the stoichiometry map. I know I've got mass of potassium permanganate, so I'm going to start here. I'm going to start here, and I'm going to label that C. Okay, then I know that my destination is mass of chlorine right here, or I could stop at moles of chlorine, because whether I have moles or mass, the lower quantity based on potassium permanganate or hydrochloric acid is still going to indicate to me which is the limiting reagent. Okay, so the path that I'm going to take is C to D, D to 4. That's the path that I'm going to take. So the mass of potassium permanganate, the moles of potassium permanganate, the moles of chlorine. And then if I want to calculate the mass of chlorine, that's the path. C to D, 4 to 3. And the conversion factor is the molar mass, to go from mass to moles, the balance equation, to go from moles of potassium permanganate to moles of chlorine, and then the molar mass of chlorine, to go from mass of chlorine to moles of chlorine. Okay, so go ahead and show you that calculation. And again, you can see that that's exactly what I did. I started with 35 grams. I used the molar mass, and notice how I have dimensional analysis, grams of potassium permanganate. The molar mass is grams per moles. The balance equation is 1 mole of 2 moles of potassium permanganate. That's this right here, for every 5 moles of chlorine. And then finally, the molar mass of chlorine is 70.9 up here to 1 mole. So when I set this problem up, everything cancels. Grams of potassium permanganate cancels, moles of potassium permanganate cancels, moles of chlorine cancels, and what I get is grams of chlorine. So that's the first part, okay? Um, yeah, Nazala, where is the typo that I had? Uh, for the mass of chlorine. Yeah, the mass of chlorine, 35 for that. And the molar mass, yeah, this is a typo right here. It should be 70.9. Ignore that dot right there, okay? It should be just 70.9, not 70.9.0, okay? Um, yeah, I think I corrected it, but then I forgot to erase that. Anyway, that's why I have it here so that it's obvious the number that you put here. But I hope you guys can follow that, because you see how dimensional analysis really lays it out. If you know dimensional analysis, then you don't, it's almost like you're not even thinking, you're just laying out the map. So that's that part. Let me just move on and show you the next part. Oops, sorry about that. Um, So this is the calculations for hydrochloric acid. Now notice I didn't even use the 35 grams of potassium permanganate, but it's basically the same concept. What I did was I started out with the mass of hydrochloric acid that was presented in the problem. Again, you're going to go from C to D, but now instead of potassium permanganate, you're using hydrochloric acid. So you need to use the molar mass of hydrochloric acid. You need the balance equation that relates hydrochloric acid to chlorine. And then this path right here, they're identical to the previous problem because it's still going towards the mass of chlorine. So that's exactly what I did. We have 45 grams. I used the molar mass of hydrochloric acid. I used the mole ratio, that's these coefficients, to relate hydrochloric acid to chlorine. And then you see how these two steps are identical? And that's because they're both going after chlorine. So the numbers are changed, and all you have to do is follow through the math. When you follow through the math, you get your calculations. Now, make sure you know how to use your calculator, because you work so hard in setting it up. It'd be foolhardy to miscalculate something that you just finished setting up. Now, if you have to turn in your work and I can see your mistake, then yeah, I'll give you credit. But in multiple choice exams, you usually don't get credit if you put down the wrong answer. And generally, at least in my exam, it's very rare. Maybe 1 or 2 problems will have no correct answers. Okay, but in general, the answers will be there. So that's the setup. Now we know that the hydrochloric acid, because it yields the lowest amount, is the limiting reagent. So we know that the mass of chlorine that is going to be be produced is 27.3. That would be your answer. The theoretical yield in this problem is 27.3 grams of chlorine that is going to be produced. The 39.3, that's an excess, okay? You're going to run out of hydrochloric acid before you can consume all your potassium permanganate. So that's why you ignore that, okay? If you want to know how much potassium permanganate remains, this is how you would do it. Let me just show you. If the question is, you've got 45 grams of hydrochloric acid and you've got 35 grams of potassium permanganate, which is the limiting reagent, which would be hydrochloric acid, and how much of the excess remains. So let me just show you how to do that calculation here. Let me clear my board real quick, because this is a problem that you might see in the future. So basically, we know that our limiting reagent is going to be chlorine, hydrochloric acid, I mean. And the amount of hydrochloric acid is 45.0 grams. So that's my limiting reagent. So I want to know how much potassium permanganate is consumed based on the limiting reagent. And the way you do that is, again, you always start with your limiting reagent. Let me move this out of the way. This is the chat. You start with your limiting reagent, which is 45 grams of chlorine. Then, sorry, not 45 grams of chlorine, but 45 grams of hydrochloric acid. Okay, for 45 grams of hydrochloric acid. And remember that in this problem, we're going to go from mass, we're going to go from mass of hydrochloric acid to moles of hydrochloric acid, but now we're going to go from moles of hydrochloric acid to moles of potassium permanganate, and then we're going to go from moles of potassium permanganate to mass of potassium permanganate. So the steps are still the same, the chemicals are just different, okay? So I just want to remind you about that. So let me go ahead and finish this. I know that the first step is the molar mass of hydrochloric acid, and the molar mass of hydrochloric acid is 36.5 grams per mole of HCl. Then I know from the balance equation that for every 16 moles of HCl, I have 2 moles of potassium permanganate. And where did I find that? I found it right here in the balance equation, 16 to 2. And then, okay, continue my calculation. I'm going to convert moles of potassium permanganate to mass of potassium permanganate. So I know that for every 1 mole of potassium permanganate, I've got, according to my molar mass, 158 grams. So if you do this calculation, and let me get my calculator out, this will tell you how much potassium permanganate is actually going to be consumed. If you take 45 and divide it by 36.5, okay, and multiply it by 2 and divide by 16 and multiply by 158, you're going to get 24.35. Make sure you do that with your calculator to double check my work, just so that again, I've been known to punch things incorrectly. That'll be the mass of KMnO4. But remember that we were given 35 grams of KMnO4. So we are going to consume 24.34 grams of KMnO4. So the amount that remains is going to be 10.65, sorry, grams of KMnO4 not used. That would be the excess reagent. And you see how in this particular problem, I basically used the same concepts that we had in the previous. I went from mass to moles, and then moles of HCl to moles of potassium permanganate, and then moles of potassium permanganate to grams of potassium permanganate. So again, the chemicals have changed, but you're still using the same song and dance. You're still using the same steps. And if you know how to read the stoichiometry map, it's always going to be that way. The questions will change, but the relationship between the chemicals is always going to go through the moles. So I hope that's clear in terms of doing that. Okay, so let me go ahead and continue on, because I want to make sure that you guys see variations of these things. Put this over here. Okay, and the percent yield is going to be, let me go over here. The percent yield is always going to be equal to the actual. The actual is when you go to the lab and then you do the synthesis and then you weigh your product. That's the actual, that's reality over the theoretical. And the theoretical is based on assuming that everything is going to get converted 100% of the time. So in this particular case, if we know what the actual the is and the theoretical is, then we can calculate a percent yield. And so let me go ahead and continue with this. This is just a problem here. So this is basically it. Um, in I apologize for that. This, it's hard to navigate sometimes. In terms of the percent yield, you can see that I actually had 10.3. That was what was collected in the lab, but my theoretical was 27.3. That's what I showed you in the previous calculation. So the percent yield is just going to be 10.3 divided by 27.3 times 100. Okay, and so my percent yield would be 37.7%. If you go into organic chemistry, if you go into the lab, is based on high purity and percent yield. If you can get a high percent yield and it's a high pure chemical, you have a good grade in organic chemistry. So let's move on. Again, this is another problem, and I'm not going to go into as much detail into this, but just walk you through the PowerPoint so that you can see that it's basically the same thing. This actually is a very good problem to go over before your midterm, because it basically has all the ingredients that I might ask you in your midterm exam. Given 392 point, uh, 392 grams of KOH, let me get my pen out. Okay, so this is the chemical right here. How many moles of KOH um, does this represent? Well, for that step, all you've got to do is convert the mass to moles. Of course, you need to know the molar mass of KOH. So that's easy enough. You look up potassium, you look up oxygen, you look up hydrogen. So that right there is just a B to D problem. It's a one-step problem because you have the mass and you're calculating the moles. Let's take a look at the second one. What is the mass in grams of 5 moles of oxygen? Oxygen is one chemical. We have the moles here, and we're calculating the mass. So it's just the reverse. We're going from D to B, but we still have to go through the molar mass of oxygen. And when we say oxygen in a chemical reaction, we mean O2, not oxygen the atom. That's why I have it right here. The next step is, if you have 392 grams of KOH and you already know the moles from this first part, so you already know the moles of KOH from this first calculation, okay? So don't redo that calculation because you already know that. If you got 392 grams of KOH and you have 5 moles of oxygen, so you have the 5 moles of oxygen, what mass of KOH is produced? So again, it's a two-part problem. This part right here, you've got to go from B to D to 4. That's the step. And then from 4 to 2. okay? Because we're going to go from mass of KOH to moles of KOH, moles of KOH to moles of um, KO2, and moles of KO2 to mass of KO2. The second part of this problem is if you're given 5 moles of oxygen, what mass of KOH is produced? So that's just a D to 4 to 2, but now we're using oxygen. So we're going from here, let me change my color. Okay, we're going from here, moles of oxygen to moles of KOH, and then moles of KOH to mass of KOH. You see how, again, if you use the stoichiometry map, it's clear to you what strategy you need to use. And then finally, what volume of water is produced? Now, water is another chemical here, so you have to involve this guy. Figure out which of these are the limiting reagent first, and then use that to figure out, you have the moles of each. So use that in order to figure out the moles of the limiting reagent to the moles of the water, because that's what you're going to use to um, relate moles of limiting reagent to moles of water. Now that you have the moles of water, you need to calculate the mass of water. And then from the mass of water, you use the density of water to figure out the volume. Of course, water has a density of 1. So if you calculate, say, something like 36.5 grams of water, if the density is 1 gram per milliliters, then it's going to be 36.5 milliliters of water as well. Now, if the density was different, then you would use the density as a conversion factor to do that math. Okay, so that's this problem right here. Again, hopefully you can see from the stoichiometry map what you need to do. If only 284 grams of KO2 is produced, what is the percent yield? Again, you have to figure out which is the limiting reagent. This right here, this question right here, 284 grams of KO2, well, that's, let me clear my map. Let me clear my mess here, okay? If you have 284 grams of KO2, that's that mass right there. How many oxygen atoms? Well, you first need to calculate the moles, and then you need the formula. Okay, I know it's not here, but you need the formula, because remember, in the to relate the moles of KO2 to the moles of oxygen, and the relationship is for every 1 mole. This is not a balanced equation anymore. Okay, you need, for every 1 mole of KO2, you have 2 moles of oxygen, the atom, because the question is the atom within, right here, how many oxygen atoms in 284 grams of KO2. So you need to relate KO2 to atoms of oxygen. And you would first need to calculate this relationship, and then you would need to use Avogadro's number to convert that many moles of oxygen to that many molecules, that many atoms of oxygen. So let me go ahead and clear this, and then I'll show you the setup. Okay. So in terms of this, let's work this problem out. The first step is to balance the chemical reaction. And if you look at this reaction right here, let's take a look and make sure it's balanced. We can see that this is 1 potassium. This is 1 potassium. We're going to save the oxygen for last, okay? Because again, when we change the coefficient of that oxygen, we only affect 1 atom. We've got 1 hydrogen here, but we've got 2 here. So we need to make this 2 right here, okay? Which means that my potassium has messed up. I need to put a 2 right there. Now, if you look, I've got 2 potassium, 2 potassium. I've got 2 hydrogens. I've got, I'll put a 1 here. I've got 2 hydrogens. Now we can balance the oxygens. I have 4 oxygens here. I've got 2 oxygens here. That's a total of 6. Okay. Here I've got 2 oxygens. So I need 4 more. The way I put 4 here is I make that 2. So 2 times 2 is 4. 4 plus 2 is 6. And now that would be a balanced equation. Okay. Make sure you have the correct chemical formula. If I give you the formula in a balanced equation, you can assume it's correct. If I give it to you as a word problem, I don't give you the written formula. I say potassium hydroxide plus molecular oxygen. You have to know how to write that down. Okay. But in this particular case, the balance equation is a 2 to 2 to 2 to 1. That's the ratio. 2 to 2 to 2 to 1. And the only time you use these coefficient is in this step right here. This step right here. Okay. That's the only time. So let me go ahead and clear this up. And let's continue on with this right here. You can see that I balanced the equation. What happened here? I thought it was a 2 to 2 to 2 to 1. Why do I have a 4 to 3 to 4 to 2? Let me double check that. That's 4. That's 4. That's 6, 7, 8, 9, 10. That's 8, 9, 10. I think I balanced the equation incorrectly the first time. That's 4 hydrogens. That's 4 hydrogens. You might want to ignore my last. I apologize for that. But apparently it's, let me go back because I want to make sure that I don't mislead you guys. Okay. I apologize for that mishap. I basically had a 2 to 2 to 2 to 1. Now, if I use that, what went wrong? That's 2 oxygens here and 4. That would be 6. That would be. Anyone see the issue problem that I had? Let me go backwards because I shouldn't be able. I shouldn't. Let's take a look at this right here. This is 4, and this is 6. This is 8, and this is 2. This is 4. This is 4. This is 4 right here. So you guys help me out as to why my previous example was incorrect. Let's see. Let me clear this up again. Let me go backwards. Okay, so that I can do this correctly. Okay, let's clear this up and see why I messed up. So we've got potassium here. See, even your instructors have snafu. We've got 1 here. We've got 1 here. We've got a hydrogen here. We've got 2 hydrogens here. So if I put a 2 in front of that, okay, if I put a 2 in front of that, that tells me I have 2 hydrogens. I put a 1 in front of that. That's 2 hydrogens right there. If I put, that'll be 2 potassiums. My oxygen now is going to be 1 here. Oh, I see the problem. I messed up my oxygen count. When I put a 1 here, that's only 1 oxygen. I miscounted here. So 2 here would give me 2 potassiums. 2 potassiums correct. 2 hydrogens is correct. But now I've got 1 oxygens here, 4 oxygens here. Okay, that's a total of 5, not 6. Okay, so don't make that mistakes. So if I have 2 here and I have 3 here, then to make that a total of 5, I use the fraction. 3 over 2 times 2 is 3. So that's a total of 5. The next thing I got to do is I got to multiply this whole equation by 2. So this will change to, let me change my pen. I apologize for that because I miscounted my oxygens over here. This will change to 4. This will change to 3. This will change to 4. And this will change to 2. So the correct ratio is 4 to 3 to 4 to 2. Okay. If so again, balancing chemical reactions is pretty critical, and you can see that I messed up on this one. Anyway, now that I have the balanced chemical equation, let me go ahead and continue on with this. Okay, that would be the correct ratio. The process of dimensional analysis is still the same. 392 grams of KOH to moles of KOH, that's B to D. You can see that, and that's the calculation. It's 7 moles of KOH. The second step right here is mass of oxygen to moles of oxygen. That's D to B. So you can see that step right there. I use the molar mass. And again, I'm using the units to guide me as to what number goes where. Here, it's grams on top, moles on the bottom. That's 160 grams. But I know that I have 5 moles of oxygen and 7 moles of KOH. So in the next step right here, okay, which is that problem, if I have 392 grams of KOH, and I already know that represents 7 moles and 5 moles of oxygen, what mass of KO2 is produced? If you look at the mole ratio, let me take a step there. If you look at the mole ratio right here, this is 4 and this is 4. So if I have 7 moles from the previous problem of KOH, that's going to give me 7 moles of, because it's a 4 to 4 ratio, that'll give me 7 moles of KO2. Okay. If you have 5 moles of oxygen, then you got to do the math. You got to use the fact that for every 3 moles of oxygen, okay, you have 4 moles of KO2. So we do the math. 5 times 4 is 20 divided by 3. So 20 divided by 3 is going to be 6.66. So the limiting reagent is your oxygen because it gives you the lower amount of KO2. So now I know my oxygen is my limiting reagent. And you do that not by looking at the fact that you have 7 moles of KOH and 5 moles of KO2, but figure out how much of each of these are going to produce this product so you can calculate the lower quantity. And the lower quantity is always going to be the limiting reagent. So let me go ahead and clear this, and then I can show you that step right there. Okay, so here it is. The path is B to D, D to 4. Okay, and then for oxygen, it's D to 4. Okay, and so here you can see that my calculation, 7 moles, excuse me for that. 7 moles give you 7, 5 moles give you 6. Now we know the limiting reagent. Then we can, let me go back. Sometimes this controller is not easy to control. Then we can calculate the mass based on the limiting reagent of KO2. And that would be using the molar mass of KO2 to do that calculation. Okay, and if you do that calculation based on the limiting reagent, you get 474 grams of KO2. Let's move on. So how many molecules of water is produced? Now we know the limiting reagent is oxygen. We're going to use oxygen to figure out the moles of KO2. Then we're going to use the moles of KO2 to get the moles of water, and then the moles of water to calculate actually, we don't need to do the moles of oxygen. We just go to the moles of oxygen right here to the moles of water. right here. So we use that balance equation because we know that oxygen is the limiting reagent. We use Avogadro's number, and now we can calculate the molecules of water. So basically what we are doing is this. We're going from here to here, so D to 4, but now our chemical is water. And then we're calculating, based on that, the moles of water to molecules of water, right there, using Avogadro's number, right there. So the path, the stoichiometry map still shows you the route to complete that calculation. So let's move on, and hopefully you guys can see that calculation. Okay, finally, what is the percent yield? Let me go back. This thing's too slow, too fast for me. Um, Here it is. That's the calculation. Then the next step for this is, if only 284 grams of KO2 is produced, what is the percent yield? We figured out the theoretical yield from the last time. That was 474 grams. So we take the actual over the theoretical, we get 59.9 grams percent. Okay. So, and this is another problem that, well, this is use the molar mass to answer this question. How many oxygen atoms in 284? So we know the mass, the moles of KO2, that's D. That's this right here. And we want to calculate the number of atoms. So we're going to go to X. In this problem, we're given the mass of KO2, but remember from the previous work, we calculated that mass, well, sorry, take that back. If we know the mass of 284, we're going to need to use the molar mass to calculate the moles of KO2. And then we're going to use the formula to calculate the moles of oxygen. And then we're going to calculate the number of atoms of oxygen. So this is the setup right here. It's going to be B to D, D to Y, Y to X, because it's one chemical. So that's the first step, the molar mass of KO2. That's the relationship. For every 1 mole of KO2, we got 2 moles of oxygen. And finally, we use Avogadro's number. So all you've got to do is the math. And that takes care of that very tedious marathon problem. Okay, so again, in review, you really want to learn how to use the stoichiometry map. Whether you use this bottom one or this top one, it shows you the path and the conversion factor that you guys are going to be using. Okay, so the rest of this are just other examples showing you other ways to do the same thing. I'm going to skip over this. You guys can look at it on your own because I think we covered the bulk of it in the previous one. Because before time is up, I really want to get to energy relationship. But look at these problems on your own and actually work it out if you can without looking at the answers. These are the strategies that you guys are going to be using to solve this problem. Here's another problem in which you have the same, well, this is the same problem actually, except it's spelled out. Okay, so you guys can just look over this and hopefully see that the stoichiometry map is always being applied to solve these problems. So take a look at that. Okay. Finally, I think, again, more examples, more or less the same, still using the stoichiometry map. I apologize for the resolution of this thing. I copied this from a textbook, but it might be your textbook. I'm not sure, but it basically tells you this, the same strategy that you would use. So I'm going to skip over this. You guys can follow along on that. What I do want to do now is talk about the next section. And the next section is very short. And then if you have any questions, I'll open it up for that. And then for those of you who are in my lab, I want to make sure that you guys know that you need to go to the lab session because your lab midterm is scheduled this week. So you need to complete your lab midterm and lab practical during the regular time that we're meeting. For those of you who are meeting on Tuesday, that's after this class. For those of you who are meeting on Thursday, that's after Thursday's discussion. Okay, so this pretty much wraps up stoichiometry, and I hope that you guys learn how to appreciate the stoichiometry map, because you guys will be using it in the future when we talk about solution chemistry and gas laws. So I'm going to close out here, and I'm going to open up another uh, part, and that other part is energy relationship. Okay, and that is, I believe, this right here. Yeah.